Okay, so hi everyone again. It's back to boring old lectures by me after a couple of guest lectures. So first thing is just a logistical thing. Your videos for the projects. Due next Tuesday. So a reminder that they're 10-minute long videos, just sort of introducing and summarizing the topic. It's 10 minutes. You're not going to have time to cover that much. But try to say something interesting and exciting for people, get them hooked a bit and so on. You can just have one person present, or you can do a mixture between different people. That's up to you. But yeah, so that's due on Tuesday. I'll send out a Piazza post with like logistical details of how to upload them today or tomorrow, probably tomorrow, once I figured out how to do that. And also, if you're still confused about things in your project or whatever, then please come to office hours today. I can't promise to deconfuse you, but I will at least try. And if I can't, because I don't know the area that well, then I will read about it and follow up with you afterwards. Okay, so that's all the logistical stuff. Now for an actual lecture. So throughout the course until now, really from about lecture 6, maybe, I forget when we first introduced it, we've always had this sort of single model of in our heads of what it means to have a quantum computer, right? Which is of course the famous circuit model of quantum computing. Okay, and the way that works is that you have sort of a load of qubits, and then you interact those qubits a small number at a time, maybe let's just say 2 at a time, using some unitary gate. So this acts on a small number of qubits. And then maybe you have some other unitary gate. And yeah, let's have these two. Let's call these different things. Some big circuit of unitary gates that's probably a lot bigger than the one I just saw. And then at the end of the whole circuit, all we're going to do is just measure all the qubits in the computational basis. Okay. You can have slight generalizations of this sort of protocol. You can imagine allowing yourself to measure in sort of different bases. You could imagine allowing sort of measurements at intermediate points in the circuit. None of them really make any difference to what you're able to do. They can all be replaced very easily by this general thing. But there are alternative models of quantum computing. Which still end up being broadly similar, but more different, more clearly distinctive from the circuit model itself. So does anyone know any examples of what those alternative models might be?
There's the measurement-based quantum computing.
Awesome. There is indeed measurement-based quantum computing, which is a very interesting one that we're going to talk about today. Anyone going to throw out any other things? Okay, I'll list some more. So we also have quantum Turing machines. basically just a generalization of a classical Turing machine where the internal memories of the Turing machine end up so the internal states of the Turing machine are replaced by Hilbert spaces by quantum processes. We have adiabatic quantum computing, which again we'll talk about a lot today. Have fermionic quantum computing. It's all the ones I have in the list at the moment. I think there's probably others that haven't thought of. But the important point is going to be that all of these are equivalent up to polynomial overhead. And it's polynomial overhead in the time that the original algorithm required. So for example, in other words, if an algorithm is possible in time t in one model, then it's also possible in time p of t in other models. Okay, where p is some polynomial. Note that this is if that polynomial is large, which can be reasonably large potentially for some of these things, then there can be a big difference between able to do something in time t and able to do something in, say, t cubed or t to the fourth or something, right? So for example, if you're trying to do Grover's algorithm, which only gives you a quadratic speed up in the first place over the naive brute force classical thing, then it's very non-trivial that you can also get a similar speed up for it in other models of QC. Like most naive approaches may well not still give you a speed up. On the other hand, if we're just interested in whether some problem is possible in polynomial time or not, say we're interested in whether it's still possible to factorize primes in polynomial time, then it doesn't matter which model we use, right? Because a polynomial of a polynomial is still a polynomial. So BQP is the same in all these definitions. Okay. Any questions about that so far? Okay. So yeah, the topic of the lecture today is just giving you guys a sort of brief overview of all these different things. Some of them are more interesting than others. So let's first do the sort of uninteresting ones very quickly, just so that you've heard a few words about them. So for example, fermionic quantum computing. The idea is that rather than having a set of qubits, you have some set of like n fermionic modes. Okay, so what does this mean? If you're not familiar with this, don't worry. But basically an example of a fermionic mode would be sort of the existence versus non-existence of an electron in some state. Right, so if you have some orbital and you can create an electron there or annihilate it there, they're your two states of the fermionic mode. And the thing that makes these things different from just a qubit, they still have two states like a qubit, but if I have operators now that act on different modes, those operators. Oops. Not doing well here. Okay. Trying to get fancy and write anti-commute in red and just ended up causing chaos. Yeah, so if we have operators acting on different modes, then they anti-commute with each other rather than commuting with each other. Okay, so that's all that is. And if you attended discussion 6 with NAM, then you have seen how we can sort of go between fermionic modes and qubits, translate between them pretty efficiently via something called the Jordan-Wigner transformation. So it's pretty easy to show that this model of quantum computing is really very closely equivalent to ordinary circuit model. But there are some ways you could conceivably physically implement a quantum computer that most naturally uses like fermionic modes rather than qubits, and it's most natural to work with the fermionic modes rather than Jordan-Wigner transform of it. But as far as I know, this sort of model is not being actively pursued. There aren't any particularly good ways to build a fermionic quantum computer. It's one of those things that has been thought about for mathematical completeness. Okay, so that's one example of a pretty boring one. Another, as I say, is the quantum Turing machine, which I'm really not going to go into detail of because Turing machines on their own, if you've ever worked with them, are bad enough. Very messy, horrible things. But basically, yeah, as I said, you replace the internal states of the Turing machine by quantum states. They evolve in quantum. Your transition function is quantum mechanical and so on. But yeah, don't worry at all about that one. So the main two that we're going to talk about today are going to be adiabatic quantum computing and measurement-based quantum computing. Okay, any questions about what I said about fermionic model, quantum Turing machines? We didn't really go into detail on either of them, so probably not many. But if you have them, now's the time to ask. Great. Okay, so let's move on. Start with talking a bit about adiabatic quantum computing. And one of the projects is going to be on adiabatic quantum computing, so I don't want to go too much into detail of it. Leave them some stuff to say. But the basic idea of adiabatic quantum computing is the following. All you try to do is you find a Hamiltonian. Can be potentially quite a complicated Hamiltonian, but just some local Hamiltonian that you can imagine, physically implementing in your quantum computer. You imagine like dialing some knobs and tuning the quantum computer so that the Hamiltonian is given by this thing. So the Hamiltonian is going to be called H1. Has a ground state, the lowest energy state. It's just an eigenstate of it that we're going to call psi 0, 1. Okay, the 0 for it being the ground state, the 1 for the fact that it's H1 that's the ground state of. And we want this ground state to give the answer to our problem. Okay, so by measuring the ground state, we're going to be able to determine the answer that we wanted. Maybe it literally is the answer we want to the computational basis. Maybe it's a bit more subtle than that, but still can easily determine the answer we want by measuring it. Okay. And then step 2, easily enough, all we need to do is find a way to prepare our system in the ground state psi 0, 1. Right, so if we can control our Hamiltonian, and we can make this Hamiltonian H1, then we can just immediately make that be the Hamiltonian, and then all we've got to do is get the system into the ground state. Okay. Fortunately, that's a bit non-trivial, right? If I just have some system in some state, it won't evolve into the ground state. It will continue to be a superposition of different energy states. They'll all evolve, doing their own thing, but the state will always only have a small overlap with the ground state. So how can we get the system to be in the ground state? And bear in mind, the normal way we get something into the ground state is we cool it down. But how do you cool it down? You cool it down by coupling it to another system, right? But in this case, if we couple it to the other system, we no longer have the Hamiltonian we want anymore because we've changed the Hamiltonian. So this is a pretty non-trivial thing to do. You need to have the system be isolated, but still be cooled down into its ground state. Okay. So the way we do it, the procedure for adiabatic quantum computing is we start by preparing the system in the ground state psi 0, 0. Of another Hamiltonian that I'm going to call H0. And we're going to assume that this ground state is simple to prepare. Okay, maybe it's like a product state or something like that we can just prepare by doing some measurements and then maybe some 1-qubit unitaries or something. We're going to assume we know how to prepare the system in this ground state of this simple fixed Hamiltonian that's just independent of our problem. It's just a like reset Hamiltonian, if you will. Okay, so that's all very well and good, but now somehow we need to change the Hamiltonian from H0 to H1 and get the system to stay in the ground state, right? And this is a bit non-trivial. If we instantly change the Hamiltonian from H0 to H1, then the state is just going to stay unchanged, right? There's no time evolution that happens. We just instantly change the Hamiltonian. It's just going to stay in the same state. So we continue to have be in the state psi 0, 0. And then, of course, we time evolution. Leave it for a while with this new Hamiltonian. It'll go to like start evolving with time. It'll become e to the minus IH1t, acting on psi 0, 0. But in general, this psi 0, 0 is going to be a superposition of a large number of different eigenstates of H1. It's not going to have particularly large overlap with the ground state. And that overlap is not going to change with time. So yeah, we haven't made the state that we want. Okay, so even though we're in the ground state, the old Hamiltonian, when we changed Hamiltonian, we just, the ground state changed, and so our state is no longer the ground state. Okay. Okay, that's a bit tricky. Need to get cleverer. Solution. Yeah, so sudden change of Hamiltonian. Can think of as providing sort of an energy kick that kicks the system out of the ground state. So it started in the ground state. It's only in one point of view that it gets changed at all. In terms of energy, it gets changed. In terms of the state itself, it just stays completely unchanged. But we now have a superposition, large number of different energy states. Okay, so the solution to that problem is to change the Hamiltonian very, very slowly. And this is where the term adiabatic comes from. Just means changing it slowly. So instead of just going straight from H0 to H1, we have a Hamiltonian depend on time. So we have it proportional to sum, weighted sum, H0 and H1, where sort of the H1 fraction gradually increases over time, and we gradually change from H0 to H1 over some very long time, big T. Okay. Turns out there is a theorem in quantum mechanics called the adiabatic theorem. That roughly speaking says that a slowly boiled frog never jumps out of the pot, right? The famous claim, which I believe is not really true. But the sort of formal claim in this case is true. So the real statement of the theorem, which is that if we start a state at time 0 being equal to psi 0, 0, then state at time t will be equal to some phase factor that we don't care about times the ground state at time t, which is psi 0, 1, plus an order 1 over big T correction. Okay, this is in the limit where we do the transformation infinitely slowly. Okay, so because the Hamiltonian is changing so slowly, then there's sort of never, the system can never get kicked out of the ground state to another state. It just ends up getting stuck in the ground state, even as the ground state gradually changes over time. Importantly, however, for the error to be small, we can need T to be really quite big. And in particular, needs to be much, much bigger than 1 over delta squared, where delta here is the smallest energy difference between the ground state and the first excited state over the course of this process, right? The Hamiltonian is changing with time. And the ground state has some energy that changes with time. The first excited state has some energy that can change with time. And delta is the smallest gap between them. Okay, so it's pretty natural to sort of think about why this delta matters, right? Like you're slowly evolving with time, and you're trying to do it slowly enough that the sort of energy being produced from the like frequency of the changing Hamiltonian, the rate of the changing Hamiltonian, isn't big enough to kick you up to the next energy level, right? If that next energy level is really, really, really tiny, then you have to do it incredibly slowly, or you won't be able to make it work. Okay. Okay, so let's see an example of adiabatic quantum computing in practice. And the example, what's called adiabatic Grover search. So in this case, it's the adiabatic version of the ordinary Grover algorithm. In this case, we have H0, It's just a very simple Hamiltonian that has its ground state be a product of plus states, a superposition over all states in the computational basis. Okay, so psi naught naught is plus tensor n. That's an easy state we can prepare. And H1 is just going to be a Hamiltonian that we don't know the ground state of. We don't know what the Hamiltonian is, but it's like a black box that we can switch to that Hamiltonian without understanding, without knowing in advance what we're switching over to, and it's just going to have be the identity minus mm. Okay, so its ground state is just equal to the state m, and m here is the solution we're searching for. Okay. Okay, so if we change from one Hamiltonian to the other slowly enough, we'll start with the state psi naught naught, which we can easily prepare. It will always stay in the ground state, and we end up in the state m, and we get the answer. We've solved the problem. Okay, so just to be very explicit, h of t, in the most naive adiabatic algorithm, would be 1 minus t over t m minus 1 minus t over t. Okay. So what we want to know is how long this would take, right? Because that's that will tell us how good the algorithm is. And that's controlled, of course, by the size of this energy gap for this Hamiltonian. Turns out you can show that the energy gap at time t over 2 is equal to 2 to the minus n over 2, where n is the number of qubits you're trying to do this on. So this is a bit of a problem, because this means that for this naive version of the adiabatic algorithm, we would need the time t to be taking it to be much, much bigger than 1 over delta squared, which is, of course, 2 to the n. Okay? But if we're time taking to do the Grover search is 2 to the n, then that's no better than a classical computer could do, right? Just by testing all the options one by one. A Grover search hasn't helped at all. Okay, so it seems adiabatic computing is being a bit useless in this case. But that's just because we were a bit sort of oversimplified with the algorithm we used. In reality, we sort of know in advance that delta is only this small when we're roughly half done. Okay, if you get away from that point t over 2, then the energy gap delta gets much bigger again. Okay. So what this means is we can speed up, rather than just slowly changing the Hamiltonian at a constant rate, we can speed up the change away from t over 2, while still making sure that our error at the end of the process is small. Okay. Turns out when you do this, when you optimize over all ways of doing the change, then you find that the time for this adiabatic algorithm is instead order 2 to the n over 2. Okay, so that is the same as the time for Grover in the circuit model. I want to emphasize that this didn't have to happen. Adiabatic quantum computing and the circuit model are not the same. They can't be converted into one another in linear overhead in general, as far as we know. But in this case, adiabatic quantum computing, that does give the same time for the Grover algorithm as circuit model. Okay. So before moving on to measurement-based QC, let me just make some very brief comments on the equivalence between this model and the circuit model. Not going to go into detail at all. Okay, so there's two things you would want to show that the computational power of adiabatic quantum computing is pretty much the same as the circuit model. So the first thing is to show that circuits can simulate adiabatic quantum computing, right? Anyone know how to show that?
You can just like trotterize your unitary evolution.
Awesome. Right. So all we do is we simulate Hamiltonian evolution using a quantum circuit. Okay. So as Zach pointed out, the sort of normal way to do this uses something called trotterization. And again, if you attended discussion 6 or read the notes after this, then you'd see how that works. Okay, so that one's easy enough, and it's actually pretty efficient. Yeah, it's not quite just linear overhead, but it's pretty small overhead to do trotterization. The other way is a bit trickier. So we want to use adiabatic quantum computing to simulate circuits. And the way we didn't do this is turns out, I'm not going to explain the details of how this works. You can construct a simple or a sort of local Hamiltonian whose ground state is what's called the history state of the circuit. So what is a history state? It's a sort of single state that encodes not just the final state of the circuit, but all the intermediate states as well. So it's a sum over sort of all time steps in the quantum circuit of the circuit state after t time steps, tensored with a sort of auxiliary clock system that is different depending on which time step we're at, and that specifically consists of t qubits, where we have little t1s at the beginning, and then big T minus little t zeros at the end. Okay, so this is just a state, but it turns out there's a way to just construct Hamiltonian, add it up, create a load of terms that just force the ground state to be this state, and then by measuring the history state, measuring the clock part, we have a 1 over t probability of measuring all ones. And then that implies that the state is the final state of the circuit. Okay, so there are clever ways to do this, but the stupidest way is just take this state, measure if you get all ones on the clock. If you don't, try the whole thing again, but that's only a polynomial overhead. It's an extra factor of t, where t was the size of the circuit. And eventually you can end up with the final state of the circuit, state of your system. Okay. So that was just sort of high level overview of the sort of stuff involved with converting between these different models. What I now want to talk about for the rest of this lecture is measurement-based quantum computing. It's a really interesting one.
Can I ask a quick question about adiabatic?
Absolutely.
So in the circuit model, we measured the efficiency of a circuit in terms of the number of gates we had to apply. Here, I guess we're measuring by the time of the evolution. Yeah. There's some confusion about, I guess, the units of energy in the Hamiltonians. That makes it tricky to compare.
Yeah. But yeah, so, you've got to put constraints on. So you could say, oh, you just make the Hamiltonian really huge, and then you can do it really fast. Right, so you got to look at the scaling with keeping the norm of the Hamiltonian fixed. I think I forget is it the norm of the Hamiltonian fixed is a function of the size of the problem, or some reasonable condition along those lines. It may not depend too much on the exact condition.
I see.
Yeah, if you're only caring about polynomial, then it doesn't matter. You just need the norm to not blow up exponentially with the size of the system, and yeah.
I see. And I guess the efficiency you get from this will map onto the efficiency in terms of number of gates when you go between the circuit models.
Exactly. So when you trotterize, then the number of gates you need is linearly proportional to the size, basically. When you're constructing this history state, then you can show that the minimum energy gap delta is controlled. T here is literally the number of gates in the circuit, and you find that the minimum energy gap is polynomial in T, and so you get a final answer that's polynomial in T for the time.
Great.
Okay.
Thank you.
Great question. Any other questions about adiabatic quantum computing before we move on? Okay, let's move on to measurement-based quantum computing, also called one-way quantum computing. And somehow, to me, this is far more miraculous than any other model of quantum computing that it works. Like adiabatic quantum computing, it sort of doesn't really surprise me that that's a way you can do pretty powerful stuff. But measurement-based quantum computing is really crazy. Okay, so how it works is the following. We just have a fixed starting state. So we use the same starting state for every algorithm. We do no unitary evolution on that state whatsoever. All we're going to do is one by one, we're going to take the qubits of that starting state and we're going to measure them. Okay, and we're just going to measure them one at a time. There's no entangled measurements on multiple qubits at once. Literally just measure one qubit at a time until you've measured all of them. And the sort of only slightly non-trivial thing I'm going to do is that the choice of what basis we use to do our later measurements. Okay, so whether we use the X basis or the Z basis or some other basis, is going to depend on the measurement outcomes of our earlier measurements. Okay, so this is the only thing that stops us just doing everything at once. Is that we need to first do the early measurements so that we know the outcomes, and we can then do later measurements based on those outcomes. Okay, and using this, turns out we can do universal quantum computing. So as I say, this is really pretty crazy stuff. This should feel weird to you. Certainly does to me. Okay. And this, unlike something like fermionic quantum computing, is actually, it's a real thing people are considering. It's entirely possible that this ends up the dominant paradigm for quantum computing. It's particularly popular for what's called optical quantum computing. So quantum computing where your qubits are photons of light. And the reason for that is that photons in general have very good coherence. They're good qubits that last a long time. But they're hard to apply unitary gates to. Right, because photons don't really want to interact with anything terribly much. They just sort of go along doing their thing until they get absorbed by something, and then you've lost them completely. Okay. Okay, so yeah, if you can work out how to create this particular starting state, measurements on photons in arbitrary bases are really very easy. You just use like polarizing filters and stuff. Then you're all good. Okay. So what is the starting state that allows all this magic to happen? Well, something called a cluster state, or more generally, a graph state. Okay. So how does this work? Let's have some arbitrary graph. Just a lattice of vertices connected together by some edges. Okay, and all we're going to do is we're going to have one qubit at each of these vertices. And then we're going to prepare a state of these qubits. Okay, and the state is going to be equal to, first you start with all the qubits in the plus state, and then you're going to apply some controlled Z gates to pairs of qubits ij. Okay, so remember, a controlled Z gate doesn't matter which gate is the control and which is the target. It just applies a phase of -1 if they're both in the one state. Okay, and we're going to apply this controlled Z gate to all pairs of qubits ij where there's an edge between I and j in a graph. Okay, so the qubits are labeled by vertices. So this could be I and this could be j, and we have an edge between them, and so we apply a control z. Note, of course, that the controlled z's all commute with each other, so it doesn't matter what order we do them in. Yeah, we just have this one state that's produced by that process. Okay, everyone clear with that? Okay, so there's an equivalent definition. These cluster states you'll often see. Which is sort of a stabilizer style definition, which is that it's the unique state with mi psi being equal to psi for all I, or qubits I, where mi here is equal to an Pauli X on state I, and then a product over all j, where ij is an edge. So all product over all the vertices connected to I by an edge with ZJs. Okay, so we have an X on the site itself, and then a J on all the neighboring sites. It's easy to check that all of these things commute, and that, yeah. So if I have XI ZJ, and then I have a controlled Z acting on those two things, that's actually equal to just the controlled Z followed by just the XI with no ZJ. Okay, so what that means is that MI acting on product over all edges of a controlled Z, as you commute it past as you commute the MI past each of these controlled Zs, then it deletes all these Zs on neighboring sites. Okay, and so that ends up being equal to the controlled Zs coming first, followed by just an XI. And that, of course, is just equal to psi. Okay, so these two definitions of the state are equivalent, but yeah, it's just a product of plus states with some phases applied if pairs of neighboring qubits are both in the one state. Okay, so that's the definition of our state. How on earth can it let us do all this crazy stuff just by doing 1 qubit measurements on it? So let's first see how we can implement 1 qubit gates just using 1 qubit measurements. I'm not really going to go into the mathematical details of how this is going to work because it's kind of messy and horrible. I'm just gonna give the answer, and if you're inspired, you can check it yourself until you believe it and no longer feels magical. But I'm really just going to state the result. It should feel vaguely believable. So let's say that we call m theta the basis consisting of the two states 0 plus e to the I theta 1 and 0 minus e to the I theta 1. Okay, so for example, m0 is just a measurement in the x basis. And m pi by 2 would be a measurement in the y basis. Okay. And let's say the unitary, we can parameterize all 1 qubit unitaries by 3 sort of angles. Okay, zeta, eta, and psi. As we saw, I think, in a homework way back when. And I'm going to parameterize them so that this is e to the minus zeta times Pauli x, e to the minus I eta Pauli z, e to the minus I psi Pauli x. Okay, so any arbitrary 1 qubit unitary can always be written in this form. And yeah, we're going to show how to implement the 1 qubit unitary just by doing these measurements. So we're going to start with 5 qubits that are going to all be in a sort of graph state in a line. It's not quite going to be a graph state because rather than having them all be in plus state, I'm going to have the one on the left be in the sort of input state that we're wanting to apply the unitary to. Okay, so we're going to have psi, tensor plus, tensor plus, tensor plus, tensor plus. And then, of course, there's going to be a CZ applied to each neighboring pair. Okay, so we're going to assume that we have that starting state. And then we're just going to start measuring qubits. And in fact, we're going to measure the first 4 qubits, and then the final qubit, the 5th qubit, is going to end up storing our output state. Okay. And all we're going to do is we're going to measure them in particular choices of basis. Okay. So the first qubit, we're just going to measure in the X basis, so the M0 basis. And we're going to do that measurement. We're going to get some outcome, which we're going to call S1. Okay. Having got that outcome S1, we're then going to measure the second qubit. But this time, we're going to measure it in the basis minus, I need to get this the right way around. I think it's psi rather than theta. I can't read my own notes. So it's possible this is the wrong way around. So now this theta here is going to be minus psi times -1 to the S1. Okay, so it's either minus psi or it's plus psi, depending on whether we got measurement outcome 1 or 0 for the first measurement. Okay, so we do that measurement, we get some outcome S2. And now we go to the third qubit. Okay, we're going to measure that in a basis M minus eta -1 to the S2. So that's going to depend on our second measurement. And then we're going to get some outcome, which we're going to call S3. And then finally, we're going to do a measurement here in a basis that's going to be minus theta -1 to the S1 plus S3. Okay, and that's going to give us measurement outcome S4. And finally, this last qubit is going to be our output state. Okay, so I'm not going to go through the details of the calculation for you. You guys can look into this more if you're interested, but you can check the final qubit state is in fact X to the S2 plus S4, Z to the S1 plus S3, U acting on psi. Okay, so we haven't quite ended up with it being the state U psi. It's not completely perfect, but it's in U psi up to some Pauli's. You know, this is either just an X or a Z or both or neither at the front. Okay, pretty easy. You know, if we're wanting to apply some unitaries afterwards, right, to carry on the circuit, then all we're going to do is just absorb these Pauli's into the definition of the future unitaries, right? So rather than just trying to apply unitary U next time, we'll try and apply the unitary U, X, Z, or whatever it might be. Eventually, we're going to want to do a sort of final measurement of our state once we've implemented the circuit we want. And at that state, we may still have some X or some Z that appears at the end of everything, but that's fine. That's not a problem, right? Because if we're measuring in the computational basis, Z doesn't do anything. That's just controls changes the relative phase between 0 and 1, and we're just interested in the probability of getting each of them. Meanwhile, X just flips the probabilities of getting 0 and the probabilities of getting 1, right? And so that's just just a matter of reinterpreting the measurement outcomes. The computational basis measurement is still the thing we want. It will give the right information. Okay. So you might also ask, what if we wanted to like concatenate unitaries together? We want to apply U1. Okay, I mean, one way we could do it if they're just single qubit gates is you could just work out their product and then implement that as a product of three things. But we're going to introduce non-single qubit gates in a minute. So let's see how we would do it. Okay, all you would do is you start with let's draw a long line. So these are all going to be plus except for the first one. Okay, and so what we're going to do is do the measurements for U1 here. Okay, and then so if we had so we have CZs on all these lines. So previously we just had this state, and we ended up with U acting on psi here, stored in this fifth qubit that didn't get measured. Now, of course, there was also CZs applied to all these things. Okay, but that CZ applied between this fifth and sixth qubit that commutes with all the measurements we did on the first four. So that makes no difference to how that all works. So we can imagine that being having been applied after we did all these measurements rather than before. And so after doing the U1 measurements, we just end up with potentially X and Z, and then U of psi here, right? And so then we just do U2 with possibly undoing X and Z if we need to here. Okay, so we can concatenate these processes together. This sort of long line graph state, cluster state, sort of acting as a time direction, right? We just all these different qubits, we're letting us evolve the state with time. Okay. So that's great, but at the moment we only have 1 qubit gates. So to get universal quantum computing, we need some sort of 2 qubit gate, and one that'll do is just a CZ gate. So this plus 1 qubit gates is universal. So there's a lot of ways to do this CZ gate, but in general, you need a slightly more complicated sort of structure to the graph. So something like this. Going to have one of your inputs qubits is going to be up here. The other one is going to be down the bottom here. Your outputs are going to be up here and down here. And basically all these qubits you're just going to measure in the X spaces. turns out that that is enough to implement a CZ gate. So these output qubits will end up being CZ gate with some potential Paulis at the front of it. Okay. So we put it all together. Quantum circuit involving sort of 1 qubit gates and maybe some CZ gates and stuff becomes some complicated thing where maybe something like this, right? So maybe we have a 1 qubit gate here. So there should be lots of dots here. I'm just too lazy. Okay, so maybe this is a 1 qubit gate getting applied. And then here we have a CZ, and there's lots of other 1 qubit gates around and so on. Okay, so we have some complicated graph, and using that particular complicated graph plus all our different measurements and all the qubits will end up giving the output qubits up the end here somewhere. Okay. Of course, we have this seems a bit problematic given what I said at the beginning. Seems like maybe we need a sort of different graph, right? So a different starting state for each algorithm. Fortunately, it turns out this isn't the case. There's a very simple trick we can do, which is that we just start with a sort of full 2D lattice. Okay, so this is called a 2D cluster state, just a regular rectangular 2D lattice. Okay, and then to get to the lattice that we want, to get to the graph that we want, we're just going to chop holes in this lattice by measuring qubits in the Z basis. Okay, so we haven't used the Z basis at all until now. We've just used X basis and Y basis and things in between the two. But it turns out, if you say measure this qubit in the Z basis, you end up with the following state. Like this. Okay, so that qubit has got measured, it's no longer there, and you just get a cluster state, except there's a Z. If the measurement outcome of this Z basis measurement was 1, then there will have been Zs applied to all of these qubits that were connected to the one we deleted by an edge. Okay, but again, that's something we can deal with by just adapting our algorithm to take into account the fact those Z gates had got applied. So this is really just it's a graph state for the graph with the vertex removed. And maybe Z gates applied. Okay, So what you can do is you can take your QED cluster state, chop out all the things you don't need, and make some sort of remaining thing that looks something like this. And yeah, then you're done basically. Then you can implement an arbitrary quantum circuit. Okay. In fact, this isn't sort of the isn't the quite the dominant paradigm people are thinking about for doing these measurement-based quantum computation things. So in fact, what's seen as the most promising approach, I'm not going to talk about the details of this, but again, you can look it up, is to instead use not a 2D cluster state, but a 3D cluster state. Okay, so just a graph state on a 3D regular lattice. And in that case, turns out you can sort of implement a version of the toric code. So you might say, wait, the toric code was a 2D lattice, why is 3D going on? Well, the reason is that we have 2 dimensions for the sort of toric code lattice, and we have one dimension that represents time going through the circuit, right? Because when you're doing this measurement-based quantum computation, then time evolution is measuring qubits and transferring the information to a neighboring qubit. Okay, so this this lets you do quantum error correction, and in fact it gives fault tolerance with one of the highest thresholds we know of. So this is actually a very promising and interesting approach. It's not the sort of dominant one, but there's startups and so on that are really pursuing this thing. Okay, so I think it's probably going to be a bit of a shorter lecture today. I don't have anything else I really want to cover for you guys. But any questions on all of that, on measurement-based quantum computation particularly, but also anything else you were unclear on?
I have probably a very dumb question.
Yep.
I just I don't really understand what these legs are, like either physically or in the context of this algorithm where we're specifically not implementing these typical unitaries and instead are doing them by measurement. What does it mean to have a CZ in that case? I guess either physically or in the context of not having typical unitaries.
So don't think of the CZ as being applied. Think of the CZ as our original state is a state where there's a CZ like applied there, right? So somehow we found a way to construct this state. And another way to think about it is that our original state isn't an eigenstate of just x's. It's an eigenstate of x's plus z's applied to all the neighboring qubits. So the legs are always there from the original
kind of entangled state.
Yeah, exactly.
Okay.
Which you can think of as CZs applied to all pluses, but it's just some entangled state that we have some way of preparing. And really one of the ways you could try to prepare it is you could try to actually measure all these MIs and then there's various ways, and honestly I don't know the details of how the optical quantum computing guys actually want to prepare these states. I've listened to talks on it over the years, but I as with a lot of experimental things, I just don't have the background to keep paying attention and appreciate the sort of stuff involved. But yeah, they have ways of preparing the state, even though they don't have good ways of just implementing arbitrary quantum circuits. Yeah. Any other questions?
I have a question, but it might be so ridiculously vague that it doesn't warrant an answer.
That sounds great. Sounds great.
I remember listening to someone else explain cluster states and measurement-based quantum computation before, and they were implementing CZ gates using Hadamards. It was like they had a contraction of 3 different legs in a tensor network sort of thing, and a Hadamard. Do you have any idea what I'm talking about?
Yeah, I think so. So I sort of glossed over this. But if you look at the sort of intermediate state, yeah, yeah, let me say, if you look at the intermediate states, sort of like what's happening is you go along the line here, right? I just claimed, oh, you just do this magic thing and it ends up implementing this whole process. Really what happens is that each of these things sort of m theta, measuring the first qubit and some basis m theta, basically applies, let me get this right, applying a Hadamard followed by e to the minus I x theta. Okay, don't. I'm not completely certain this is right. I need to have it written down. But basically, what's happening? So this first M0 measurement in its x basis just applies a Hadamard, and then yeah, a Hadamard. You know, maybe you have some x or some z's depending on the measurement outcome. And so the way you're implementing this unitary is that this is equal to let's see. Hadamard squared e to the minus I psi x, Hadamard e to the minus I eta x, Hadamard e to the minus I zeta x. Right? Yeah, so we have two Hadamards at the beginning here. Okay, so this first measurement in just the x basis, that's just trying to apply this very end Hadamard. Then the next one is applying the Hadamard and the e to the minus I psi x. The next one is applying the Hadamard and the e to the minus I eta x. The next one is applying Hadamard and then the e to the minus I zeta x. Okay, and you're using the fact that the Hadamard constantly switches like x and z, and so you can implement both the ETI z's and the ETI x's using the same sort of measurements. Yeah, and always, all of these things, you know, there's Pauli's getting left over. That that's why these measurement bases are needing to depend on the previous measurements. Does that maybe give you some answer to your question?
I think it's closely related. The thing I was trying to imagine is it was just a very pretty way that someone had drawn this cluster state in 2D using Hadamards, but this might.
Oh, for constructing the cluster state. Ooh.
Yeah.
I mean, I guess they're using the Hadamards to construct the pluses. I don't know that, I'm afraid. I'm not an expert on this topic whatsoever, so there is a lot about it that I don't know that well. Yeah,
it's a very big question.
Yep. Oh, good. Any other questions? Okay. Well, if that's it, I think might leave it there. Let you guys go 5 minutes early. Thanks all.